Why do metal ships float and metal coins sink? And why does adding just a little bit of air to your BCD suddenly make you rise? The answer is part skill and part physics. It's about understanding buoyancy and how that's affected by Archimedes' principle. Well, hello everybody and welcome back to Scuba Science, our 20th episode since we started the series last year. Today we're going to talk about Archimedes' Principle, the law that controls buoyancy in scuba diving. If you're looking for practical tips about controlling your buoyancy, there is a Scuba Science video right here on the DiveSAGA channel talking about buoyancy. In this video, we're diving into a little bit of the math behind Archimedes' Principle and buoyancy. Before we dive into the math, I need to give you a little bit of background as to how Archimedes' Principle came to be. Around 250 BC, King Herod II of Syracuse asked Archimedes a tricky question. Did my goldsmith trick me by mixing silver into my gold crown? The problem, the crown could not be disassembled or melted into its constituent parts. So Archimedes had to find a way to figure out how much gold and or silver was in the crown without changing its structural integrity. Archimedes was pondering this problem as he lowered himself into his bathtub and noticed that the more he sank into the bathtub, the more the water level rose. And that's when things started clicking. The more he lowered himself into the bathtub, the more he displaced water. By displacing water, he was able to measure the volume. Gold is very dense, silver is less dense. So a crown with silver mixed in would have more volume than a crown that is pure gold. The more volume, the more displaced water. Archimedes had figured out a way to measure the volume of the crown without disassembling it. Legend says he jumped out of the bathtub and ran through the streets naked, shouting "Eureka!" or "I found it." And that is supposedly the birth story of Archimedes' Principle, which states an object in a fluid is pushed upwards by the weight of the volume of water that that object displaces. In diving language, that means that water pushes you up with the same weight of the water that you displace. So if you displace more water than your own weight, you will float. If you displace less water than your own weight, you will sink. And if the amount of water you displace weighs as much as you do, you will be neutrally buoyant. That is the core principle of buoyancy. So let's use some easy numbers to explore the math behind Archimedes' Principle. Because freshwater and saltwater have different weight, the math is going to be slightly different. So let's start with freshwater. For this exercise, we will assume that the freshwater we are diving in is 1 kilogram per liter. So if your body and the equipment that you are wearing all displace about 80 liters of water and every liter of water weighs 1 kilogram, there will be an upwards force of 80 kilograms. This is 80 kilograms trying to push you up out of the water. Now we need to compare this to your total weight, you plus your scuba equipment. If that total weight is, let's say, 78 kilograms, then the downwards force, your weight, of 78 kilograms is lower than the upwards force, the weight of the water you displace, which, as we said, is 80 kilograms. So you will be 2 kilograms positively buoyant. If you now start adding lead weights to increase your total weight, and we ignore the minor addition in displaced volume of water that these weights cause, if you add 2 kilograms of weight to yourself, you will now have a total weight of 80 kilograms. Remember that the upwards force was also 80 kilograms. You are now neutrally buoyant. If you add more weight to yourself beyond that, you will weigh more than the water you displace and you will become negatively buoyant. So there's no mystery here, just your weight and the water volume you displace and its weight. That's Archimedes' Principle. The example gets a little bit more tricky in saltwater, but we're going to explain that in a minute before I tell you about our partner Divevolk. Divevolk produces housings for smartphones, and if you do watch our episodes, you see that I actually use them regularly as well. They're great for taking quick pictures underwater, even shooting video. I even use them for watching videos during long decompression times, because in the back of the housing is a fully flexible screen that allows you to use the touch screen of your smartphone. It's super durable and fully waterproof, and you can actually use most features on your phone during the scuba dive. This is a great way to start practicing underwater photography and videography without breaking the bank and buying an underwater camera. So if you are interested in picking up a Divevolk housing, I'll put a link below. You actually get a discount on the product, and it does also support the DiveSAGA channel and Scuba Science. Now let's talk about Archimedes' principle in saltwater. Saltwater weighs slightly more than freshwater. Again, Archimedes' principle states that the upwards force equals the weight of the displaced water. If we assume that saltwater weighs about 1.03 kilograms per liter and you displace 80 liters of water, we simply take those 80 liters and multiply them by 1.03, giving us 82.4 kilograms of upwards force. So indeed, the upwards force is slightly higher in saltwater than in our previous freshwater example. If you, the diver, with all your equipment weigh 80 kilograms and displace 80 liters of salt water, your downwards force is 80 kilograms, but your upwards force is 82.4 kilograms. The force that's pushing you up is slightly higher than the force that is pulling you down. If you were to add 2.4 kilograms to your system and, for the sake of convenience, ignore the tiny additional displacement that causes, then you will be perfectly weighted for this type of water. For your total weight will be 82.4 kilograms, and the 80 liters of seawater that you displace also weighs 82.4 kilograms. These two forces being equal means that you will be neutrally buoyant. If you add more weight onto your person beyond that, you will become negatively buoyant and sink, because you will weigh more than the water you displace. So how do buoyancy control devices play a role in all of this? Well, buoyancy control devices simply serve to increase your volume. When you add air to the BCD, you increase your volume and therefore displace more water. If you displace more water, then of course the weight of the water displaced will also increase. In other words, the upwards force becomes greater than the downwards force. So let's say that you increase your BCD volume by 2 liters, then your total displaced volume will also increase by 2 liters. In fresh water, that would mean that you create an additional upwards force of 2 kilograms. So simply put, with the press of a button on your BCD, you can increase or decrease the upwards force caused by the displacement of water simply by increasing or decreasing your volume. If you're properly weighted, that also means that small incremental changes should be enough. Now let's combine everything we know about Archimedes' principle with everything we learned about Boyle's law in one of our previous episodes. Boyle's law states that as the depth increases, the pressure will increase and any volume subject to that pressure will decrease. In other words, any amount of air that you add to your BCD will shrink in volume as you descend, as the pressure on it increases. A direct result of that is that if you put any amount of gas in your BCD and start descending, that volume of gas will start shrinking and the displacement will decrease. In other words, whereas the same amount of gas in your BCD might create neutral buoyancy at one given depth, it might lead to negative buoyancy at a deeper depth, simply because the volume of that gas has been decreased. So if at the surface your BCD hypothetically contains 4 liters of air, that will equal 4 kilograms of displaced fresh water. But as soon as you descend to even 10 meters, that volume will be halved. So 4 liters of air in your BCD at the surface will only equate to about 2 liters of air in your BCD at 10 meters, meaning only 2 kilograms of upwards force. And that's without touching or correcting anything. So it speaks for itself that as you descend, you might have to create additional displacement by adding extra air to your BCD. That's just physics and a result of Archimedes' principle as we apply it on our buoyancy and our diving skills. Now that you understand the math examples, you should also be able to understand how weight is going to affect our buoyancy. If your body plus the dive equipment that you are wearing creates 85 liters of displacement, but your total weight is, for instance, 87 kilograms, then you will of course sink. You might in fact be overweighted, and for you to compensate for this, you would have to find a way to remove about 2 kilograms of weight from your person. So proper weighting in scuba diving is really just a matter of matching your total weight to the weight of the water you displace. Of course, this is not very practical, so in reality, conducting proper buoyancy checks and weighting yourself accordingly is just much easier. But at least it gives you a mathematical idea of what neutral buoyancy actually means on paper. So in conclusion, Archimedes' principle states that the water pushes you up with a force that is equal to the weight of the water that you displace. This explains why you might float or why you might sink. It explains why the same weight makes you less negatively buoyant in salt water than it does in fresh water. It explains how to achieve neutral buoyancy and how adding and removing air to and from your BCD affects your buoyancy. So buoyancy is not a feeling, it really is math, it is a calculation. While in reality you will still conduct buoyancy checks, it is important to understand that this is not something approximative, it is absolutely quantifiable. It's scuba science.
If you're into scuba diving, make sure to also follow the DiveSAGA Dive Debrief podcast. You can find it on Spotify and YouTube. In this podcast, we cover the behind the scenes of our DiveSAGA episodes.